Okay, so my lectures, and I think all the lectures in this school will treat this subject, topological states of matter, various descriptions of it with different mathematical setups as a subject of mathematics. But nevertheless, I think it's a good idea to keep in mind, and maybe not for everyone personally, but certainly for the subject as a whole. I think it's important to keep in mind that we're doing this because there exist physical systems, either materials or manufactured systems, that show these amazing phenomena that involve topology in one or another way, that show us that matter at very low temperatures under certain conditions can be in very entangled states that are relevant for how they behave and the response that these systems give to perturbations, transport properties, and so on. It's also the basis for quantum information science. If you build quantum devices that can do useful things, that can really show the quantum experiment that it will be because of these substantially entangled states and the properties of them that we like to understand mathematically. So I'm not going to talk much about physics, but just to tell you at least where the interest in lattice systems comes from. These are many-body systems, and they generally have different components, which may have varying degree of importance. So there are usually atoms with internal degree of freedom, So these are what we call spins or qubits. So these atoms are often located at certain regular positions in space. And so we use a lattice to indicate the coordinates of the lattice. It could also be a graph that is somewhat more or less meaningful, or but not directly related to space, indication of who's near or who's in communication with who in a device, in an optical lattice or something like that, or in a quantum device that people are trying to build. And so these are the atoms. They have spin variables. They may also exchange particles, electrons, typically. So in addition to the what I call their atoms, the spins or the qubits, there may be fermions, in principle be bosons. These are electrons. And they can move from one atom to the neighboring ones. So that's a second type of degree of freedom that we can have in our system. And there can also be phonons. When these locations are really locations in space, they're not truly fixed. Imagine that they're fixed, and most of the time we will sort of ignore this, but there is definitely systems where it plays an important role or plays an important role in setting up the interactions that the spins and the fermion degrees of the field experience. So you can think of them as little springs that describe the interaction between the atoms, but it's a quantum system. And they are bosonic particles, quasi-particles, called phonons. I will not talk about those. I will not say very much about these. I will mostly focus on the description of spins. So all these types of degrees of freedom may play a role. Very often, what we're really interested in is happening in just one of them, even though the presence of the other may be important. And the truth is that the mathematical formalism to describe spin systems or lattice fermions are very similar. And there are a few small important differences. And I don't think I will have much time to talk about it, but I just wanted to mention this. you will hear about fermion systems from the other lecturers. So I have actually updated my goals for this series of lectures a little bit, and after learning what other lecturers will talk about, and I decided that the most important thing for me to do would be to stick with the basics and the general setup and the framework that we use to describe many of these important problems. And so that's what I'm going to do. So I'm going to assume that you know the very basics of quantum mechanics. And then when I say Hilbert space or Banach space, I don't have to explain metric space and so on. If there are specific things, terminology that I may be using in a slightly different way than what you're used to in your field, you can certainly interrupt me. Absolutely feel free and ask questions. I have to figure out exactly what to do. I'm not sure what Anton referred to with the slides. This was so to be able to present them more easily, whether they are then also posted publicly, or at least for the participants, I don't really know. Is that the? I think that's sure. Yes, let's figure it out. So what I would like to do, I don't have complete lecture notes. What I would like to do is to give you a list of references and some comments where you can find more information, either the more elementary part or the papers where the full technical details are wrote down, if you are interested. Okay, so we'll post you about that when it's available. Okay, so let's move right away to the general setup. So I'm going to release this with just a background comment. Something I don't want to forget, and I think you shouldn't forget. So the general setup for quantum spin systems. So we'll describe what is often in the literature referred to as bosonic lattice systems, but it's really spin systems. And what is important is that the Hilbert space associated with each degree of freedom, with each spin or each atom, is a finite dimensional one. And the lattice, in fact, I'm going to take to be a discrete metric space, and I'll explain what I really need for the description. So it's not a lattice in the mathematical sense. It doesn't have to be a vector space over Z or anything like that. But these are the points that either label the spins and represent, if it's a physical system, the spatial location of the degrees of freedom. So we're not doing particles in Euclidean space or Minkowski space. It's a discrete version of space that we are using. Time, however, will be continuous. So discrete generally means that balls of radius, a finite radius. So this is the ball of radius r centered at x. Its number of points is finite for all x and gamma, and are greater than 0. But I'm going to add some additional properties in a second. So that's sort of what I would mean by discrete. We will often assume a little more. So plus something like through regular, which is one representation of the idea that it's a finite dimensional space, finite dimensional lattice. It means that it exists constants kappa and nu, such that these balls Bxn, the number of points in them, doesn't grow faster than some power of the radius. That's what I call new regular. And sometimes, for instance, in the works of Anton and his co-workers often assume that the space is Delaunay, which means that this gamma is embedded in our nu for some nu, and that we have an upper bound for the minimum distance to the closest point to any point, and a lower bound on all the distances that occur between points in the lattice. So, so this is not always needed, but we can assume this so that we quickly write down what it means. The terminology appears. So the distance, the metric then, we take the Euclidean metric in our nu, and then we can define epsilon as the minimum distance. So this is going to be the increment of x different from y, distance between x and y. And we're going to assume that that is positive. And then will also be delta, which is the super over all points x in our nu, and then an increment of y and gamma of the distance between x and y. So from every point in our nu, there is a point of gamma no further away than delta. And this is not always needed. But sometimes convenient to have, and that's why it's there. I should not. Oh, no, you can see. Oh, yeah. I think this is still visible for our friends overseas. So often people just formulate results where Z nu, the regular two-dimensional integer lattice, is sort of a stand-in for a space of this kind. And it's usually not very important in the sense that it's easy to generalize if you want to. But there are some instances where sort of the details matter. And so I wanted to be aware of that. Okay. So these are quantum systems. So let's talk about observables. They didn't tell you what the possible kinematics are that we have. So for every x in gamma, we have a finite dimensional quantum system. We will have an algebra AX, which is a copy of the square matrix algebra of dx times dx matrix with the complex entries. And you can also think of a Hilbert space to be a copy of C dx at every side. And then I'm going to consider finite subsets of gamma, which I will sometimes denote by lambda in P0 gamma, the sets of all finite subsets of gamma. Gamma in general will be infinite for interesting applications. At least I have to allow that possibility. Then the algebra of observables is just a standard tensor product of these algebras of each side. So this is just another square matrix algebra, right? This is something you know very well. I can define similarly the Hilbert space. Just P0 and linear transformations on that Hilbert space. So P0 is the finite subsets. Oh, sorry. I'm supposed to set that. Yes. I'm sure people use finite subsets. A lot of them are follows, and they may have other notation for it. So the point of view we've taken is we know very well what the mathematically formulated laws of quantum mechanics are that we have to apply, at least as long as this finite quantum systems, we know for each component what it is if you have a finite number of such components, you have a tensor product structure, and so there is sort of no ambiguity. It's when we consider infinite systems or study the asymptotics, the limit of the size of the system going to infinity, that on the one hand, interesting thing happens. On the other hand, mathematical subtleties may occur. And these two are, of course, related. So, but as far as a finite system goes, so suppose I have these two finite symptotic. Let's start with finite. Then the algebra of the larger one is the algebra of the smaller one. That's another algebra, but at least after identification is isomorphic. And this allows me to consider the algebra of the smaller one as a tensor factor in the larger one, right? Where the embedding just occurs by tensoring with the identity on the additional factors. So these are the, I consider these matrix algebra the C-star algebra with units. These are all C-star algebra with units. This makes it an embedding of C-star algebra with a unit. And then the local observables associated with the full system gamma is the union over all finite subsets of a lambda, since they are embedded. This makes sense. Oh, I'll put the name. So this is the algebra of local observables. Strictly local observables, some would say, and the fact that there's a name for it suggests that this is not everything that we are interested in, and that's useful. So it's a normal star algebra. It's very nice in many ways, but it's not complete. And you can imagine that this causes you problems mathematically, and in particular, it is not possible to define the dynamics of an interesting quantum system on the algebra. So we need to complete it. So A gamma is going to be defined as the completion of these local observables with respect to the norm, the C-star norm that I have. And so this is the standard completion as a metric space. And so for concreteness, this means that every A and A gamma and every sequence, so if I have a sequence of lambda n's that are finite, that increases to gamma, exists a n in A lambda n in these finite system algebras observables, such that the norm A minus A n tends to 0 as n tends to infinity. Okay, that's what you get by completion. As it will turn out, this locality structure and this fact that you can approximate observables by ones that are local plays a very important role in the basics of the physical phenomena and the mathematics that we do. And we will actually have to refine a little bit and consider algebras of observables that somehow are in between local and quasi-local, which have better approximation properties, namely where I can say something about the speed of convergence of this approximation, which here is arbitrary. Any speed of convergence occurs. Will do. It can be arbitrarily slow. But I'm not going to do that now. In view of what, for instance, Peter is going to talk about, I think I should proceed and try to get to ground states as soon as possible.
So the epsilon getting at the end, and then I don't know which row. So it's slash.
an increasing sequence.
Gotcha.
So the finite sets increasing, and the union is equal to gamma.
Okay, thanks. And Bruno,
Yes.
that this small gamma is called algebra for the local observables.
I didn't say it, but I should.
Because you use the word, but you can define it.
So far, I've only used very standard terminology. It's been done for a long time. Many people use local observables, quasi-local observables for the obvious. There will be a little bit more terminology if when we are more precise of different rates of approximation by the local observables and so on. This will happen tomorrow. Okay, so I probably should give you examples, not in any kind of detail, but sort of two examples that that's probably not need for a while. Ideally, I could give you sort of these two basic examples and keep adding to it as we go, as we introduce more and more notions. They're both very famous, and you probably all know them. One is the AKLT chain. This was introduced by Affleck, Kennedy, Deep, and Vasaki. But most of you, an infinite amount of time ago, 1987, I believe. And it's a spin-1 chain. So chain means that the gamma is Z, is the one-dimensional discrete lattice. And spin-1 means that the dimensions at every side are equal to 3. And the basic observables are the generator of the three-dimensional representation of SU2. I don't know whether I should, we don't need them now. I'll talk about Hamiltonians in a second, but let's just proceed. So the other one is the toric code on the two-dimensional square lattice. You can define it on other lattices, other gammas, due to keep time. I think 2003, more or less. I don't know exactly when we first introduced it. And there is, so there the gamma is the most natural way to introduce it, is the set of edges of Z2 as a graph. Where the edges are the nearest neighbor points. They're the nearest neighbor points on the graph. And then, so different ways to describe it so that the points of gamma can think of as being located here on the edges, whatever atoms we have that we presented. And then it's all the qubit, which means that dx is equal to 2 for all x.
Sir, can I ask a question?
Yes.
I don't, on the right board, I don't understand what you mean because you're saying the difference between A and AN, but we don't know where A is. You're defining where A lives.
For any A, that's true. So I can take a sequence, any sequence that eventually absorbs all of the lattice gamma, and any A in the completion of the looping.
Oh, that's okay.
Right?
I see.
But any such A and any such sequence that you choose, you can find approximations.
Okay.
Okay.
Gotcha.
So because that's a general, not surprising, you can't say much more about it, just that it converges. Okay. Yes.
A little bit.
Question?
Yes, sorry. Would it be possible to raise the top board a little bit? It's hard to see on the screen from the shade, the shadow.
Yes.
Thank you so much. Sorry.
Perfect.
Okay.
Thank you.
All right. So these physical systems are the most important and direct way to characterize them is by their dynamics. And as I said, you know very well how the dynamics of quantum systems is described. It's generated by the Hamiltonian, at least if you have an isolated system. And so we need to start there. And it's a interesting dynamics, means we have all these different components of our system. They're going to be interacting. If they would all evolve independent of each other, then we could just study one and there'd be nothing very much interesting to say. So we have our local observables, quasi-local observables, and we are now going to define an interaction, which is what we need to define a physical system. So an interaction phi is a map from the finite subsets to the local observables, such that each of these takes values Tx actually is in the algebra associated with X, and they are salvageable. For all X. So that's what we call interaction. Move this a little bit, maybe. And so the idea is that I can have a contribution to the Hamiltonian, which I will use for the local Hamiltonian. Associated with combined with lambda is the sum of all terms of all interaction terms associated with subsets of lambda. Okay, so see each of the phi x are salvageable with emission matrices. I get a big emission matrix, and I can use it to generate the dynamics. U of t, which is e to the negative I t h lambda. But I won't actually use the U of t very much. I will use automorphisms of the algebra of observables in lambda by taking the adjoint action ut star a ut. So that is going to be a star automorphism, to use big words, of the matrix algebra a lambda. So this is for, but in fact, since I already have my algebra of quasi-local observables, if you want, you can use this formula for every a in big A. It's an algebra after all. These U's are, the U's themselves are in a lambda, but that's a subalgebra. So that is the Heisenberg dynamics. See what has nothing to say about this. This is not the most general definition. If you think about the physics, and you say, well, you consider finite systems, there are maybe different kinds of boundary conditions you consider, and so on. But what I'm interested at the moment is taking the limit and discovering what the dynamics is for the infinite system. And so this will not be possible to do for any interaction. I will limit it. So if I just take this definition, that will not be enough. And I will give precise conditions when we talk more about the tools that use the locality properties later. But for now, let's look at a specific sort of interaction. So let's call it the definition if you want. An interaction phi is called finite range. If phi of x is equal to 0, whenever say the diameter of x, so if it exists some constant r, such that phi x is equal to 0 if the range exceeds r. So maybe there are contributions from a number of finite sets, but none of them that give a non-zero contribution to the Hamiltonian, the non-zero value for the interaction, contain points that are distance more than r apart. So you could call R the range, but there's other ideas about what the range of the interaction exactly is, but the concept of finite range interaction is unknown. And for those, you'll be able to prove that so this to keep this visible, I need to keep it here. I think it's time to erase some stuff. Okay. So for now, let's consider finite range interactions.
We'll probably want to assume that 5x is bounded uniform limits.
Well, I definitely want to assume more. But yes.
Whatever you want to do.
I will come to that in a second.
Don't understand the question.
No, it's a very good question. It means I have to say something. I will. This was like perfect. What else is here? The examples. There's not much here. EKMT mode. Toric code on Z2. You will hear more about it later. Okay. So I'll formulate it as a theorem. It's not our best theorem, but here it is. So the setup you have, suppose P is finite range. And uniformly bounded means that there exists a constant n such that the norm of Px is less than m for all x. Then for all e and a gamma, I'll maybe write it like this. The limit of tau lambda EA exists and defines a strongly continuous one-parameter group of automorphisms of a gamma. I will discuss a more general theorem in a later lecture, but this is already something that applies, for instance, to the examples that we mentioned, the AKLT model and the rhetoric code model. So let's see, maybe we can explain a few terms. And I think it's people in Cambridge or elsewhere, you have to complain that there is a part you can see. I think this should be fine. So star automorphisms, these are automorphisms of the C-star algebra. This means what you think it means. It's a bijection that preserves all the properties that define the C-star algebra. The Heisenberg dynamics, which is this adjoint action of this exponential, which you can define. It's matrices, and any way you want, the series or spectrally or ODE, whatever. It's going to be a group, one parameter group. And t is equal to 0. This corresponds to the unit element. And so the same will be true for the limit. And the strong continuity means that for every A, the map from T is good. To tau TA is continuous in the norm of the. And so why is this so good? Well, it's good for many things. I mean, we would have left the realm of physics if we didn't have any continuity. But let's be a little bit more concrete. And let me just also introduce maybe another piece of terminology. Whenever you have this could be a gamma, and this could be some one parametric group of automorphisms that are strongly continuous. This is what is called a C-star dynamic system. So let's see. In the interest of time, I will not now define the Hamiltonians for the AKLT model, the rhetoric code model, which in any case you probably all know, but they give you concrete examples of C-star dynamical systems that describe an infinite quantum spin system. So what you get from the continuity is that this group has a generator, which is a densely defined and in general unbounded map. So from the general theory of strongly continuous one parameter groups, semi-groups, so that exists as generator delta, which is densely defined on a domain from delta, which it is a closed operator. And the domain is exactly the A for which this map from T to tau TA is not just continuous, but is differential. Okay, so this domain delta is the A's and the gamma is also strongly. So the definition of derivative, you remember, and you have convergence and more. And then on that domain is just defined as the derivative. And I'm going to use the convention where I divide by I the derivative of tau t of a in e to 0 to define delta. Okay. Didn't go too high, so otherwise cuts off. And so there's various ways in which you can think of tau t as IT delta, but I'm not going to go into the technicalities of what this exponentiation means here. In the list of references that I will post for you, there's a link to lectures by Daniel Spiegel at a school in Boulder last summer that discusses this in quite some detail. It's general old stuff, like important for in this context. Okay, and since we have star automorphisms here, delta is a derivation, a star derivation, which means that we have defined that the delta of a star is negative delta of a star, and delta EB is delta A times B plus A times delta B. And of course, if you do this for the finite system, what you get is I times commutated with the Hamiltonian, which is the generator of the Heisenberg dynamics, and it's obvious that it has these properties. No I, sorry, no I. That's fine. I divided by the I. I removed the I. If you like another convention, I have no objections, but it's sort of just commutated with the Hamiltonian. It's an easy thing to remember. Okay, so why do I want this generator? Is because I'm going to use it to define ground states. So is it just like this is still coming from? So so in finite system, it's a commutator with an algebra element. And so it's naturally has capital derivation, has a lattice. And you get it for the limit. You can also derive it from the properties that it's an automorphism. Okay. Ground states. So again, in finite systems, we know perfectly well what we want. We want minimum energy states. And these are the interesting states to study because that's where these interesting physical phenomena, these topological states of matter occur at very low temperatures. So we are interested in the minimum energy states and there may be some elementary excitations about it, primarily. Okay. So, well, if I talk about states, for finite systems, I know what I mean there. Finite lambda. The state of K lambda is in general given by a density matrix, or maybe be given by a vector. Density is acting on the Hilbert space by the dimension. So this is a positive definite matrix of phase 1. And there is the special case where rho is of rank 1. where C is a unit vector in the Hilbert space. That's the case of pure states. These are the states C of ordinary quantum mechanics. This direct notation. We don't know. I can explain you, or I will refer you to notes where this is explained in detail. So I'm going to switch now. Let's put this up.
Can I quickly ask a question?
Sure.
Is it clear that the infinitesimal generator is given by the commutator with like h lambda sufficiently large on the global observables?
Yes. For the case where you have finite range interactions, this is what it is. When you go to infinite range interactions, there's a limiting process there. It is, however, not so simple to start from that definition of the generator and then use it to claim that you can exponentiate and get a strongly continuous group of automorphisms. I mean, there's some things, there is open problems there that, in fact, people have struggled with for some time and mostly given up. But if you start from the automorphism side, you sort of have less of a problem.
I guess we just say that in your definition, domain of delta is just some complicated subset, right? But if your A is actually in the algebra of local observables, then
The action is very simple.
you can give this whatever they call it.
Right. So, okay. So for A, in local range. So say if A is in some A lambda, and in the range. Well, I haven't defined range, so I can say that it exists lambda prime, such that delta of A will be the commutator to the Hamiltonian defined lambda prime. Where basically lambda prime has to be a fattening of lambda with a distance proportional to the range of the interaction. So that all terms that phi x will produce to define Hamiltonians in even larger set, they will actually commute with A if A is in the algebra of theta, lambda 6.
And your comment just was that like just defining delta this way and then sort of closing it and exponentiating, that's harder than just defining the semi-group and then deriving
Right.
filters.
Well, in fact, it can be done that way for finite range interactions. And I think it's in Daniel Spiegel's notes. It's explained in detail how to do that. But from the moment you have infinite range interactions, this is just too complicated. Well, I don't know. Maybe there's some elegant way of doing it that nobody has discovered yet. Okay. But certainly going through the group sort of bypasses technicalities like that. Okay. So so what are states now? If I go to the infinite system, observe that what do I use states for? I haven't really said that here. Should have. The expectation in the state is A0 of A. So for any observable in A lambda, I have something called the expected value. And it's given by this. So A as a function of A, it's a linear function. It's obvious from this formula. Since rho is positive definite, positive A will get positive expectations. It's a positive function. And it's normalized because ratio of rho is 1. So if A is the identity observable, then its expectation will be 1. And so a state is going to be a linear functional omega of a gamma to C that is positive and normalized. Positive means that omega of the positive element in the C-star algebra is non-negative. And normalized means that omega of the identity is equal to 1. So these are also the fundamental properties that you have for expectations of random variables in probability theory. Not a great. So that's what the state is. Now, what about ground states? I think. Here's this board. See, can get away. Nice. So, you know what states are? What about ground state, minimum energy states? So for finite lambda, H lambda is an emission matrix. I can look at its spectral decomposition. Say I from 0 to capital N, lambda I EI, where lambda 0, lambda 1, so on, are the eigenvalues of H lambda, and PI are the eigenprojections, the spectral projections corresponding to it, have the spectral decomposition. And so what I'm interested in is ground states, minimum energy states. And what that means is, so rho, a density matrix. I think of the state as a density matrix. So now I have generalized these properties. If you go back, you apply this definition to the finite case, you get exactly these linear functions, and they are exactly in one-to-one correspondence with the density matrices. And so what density matrices are the ground states? If E0 rho is equal to rho, or depending on the range of rho is subset of the range of P0, which is the span of all eigenvectors with the smallest eigenvalue. That's what the ground state is. It's not entirely obvious how to generalize this, but because I don't have a Hamiltonian for which I can do spectral theory, at least a priori, I don't know, right? What I have is this derivation which generates the dynamics. Certainly, it should have all the necessary information, and so I can define. I'm going to use it to define ground state. So, given the system, so the state omega of the C-star dynamic system, A tau E. Maybe it's A gamma. This definition is valid for any C-star dynamic system. We have the ground state. If omega A star delta A is non-negative for all A in the domain of delta, where of course delta is the delta of the dynamics. So there's only a few minutes left. Probably shouldn't start my first lecture by going over time quietly. But it's probably a good place to start next time. But let me. So part of the motivation is very simple. If I apply this definition, it's just an equivalent definition. If I apply it to finite system, it gives me exactly the same density matrix, the same conditional density matrices. If it's also, if I take weak star limits of ground states of finite systems associated with lambda, I get lambda go to infinity for the same interaction. The limiting states are all going to be ground states for the limiting dynamics. Okay. So that's also good. There are some more explicit properties that will make the case even stronger for this be a good definition. We will talk about it next time. And we'll also then talk about the examples, and we will see what we get as the ground states of the infinite system in the case of the equality model and the toric code. So I'll stop here.